Hello, am I audible? Can someone confirm?
Yes, ma'am.
Okay, okay, great. So, yeah, okay, thank you. So let's wait for a few minutes because I can see that people are still joining and then we'll start the session, okay?
Sure, sure.
Okay, maybe we can slowly start the session. People can continue joining. So, hello everyone. I hope I will just share my screen. Sorry. Okay. So, hi everyone. So, first of all, thank you all for joining on holiday and happy Republic Day to everybody. So, first of all, let me introduce myself. My name is Zenia. I am a PhD student and Prime Minister's Research Fellow at the Indian Institute of Science. I primarily work as an astrophysicist. I study the properties of very extreme sort of compact objects that exist in our universe, like white dwarfs and neutron stars. And this has a lot of intersection with particle physics, which is why, okay, if you are not having any doubt, please mute yourself. Otherwise, it's kind of disturbing. Okay, anyway. So, yeah, so my name is Zenia. I am a PhD student at ISC and I work in astrophysics. Particularly, I study these objects called neutron stars and white dwarfs, which are compact objects. They are formed at the end of stellar evolution. I can talk about them some other time. But the important thing is that these objects are where matter exists in very extreme properties. And that's where the intersection happens between what I do and this course, which is, of course, about particle physics and the standard model. So, essentially, if we need to understand how matter behaves at extreme conditions, we need to first understand how matter behaves at those normal conditions that we see around us. Then we can extrapolate to extreme conditions like within the cores of neutron stars, where the density can be many times that of an atom, and so on. So that's why, for me at least, particle physics is a very important part of what I do because I'm trying to study the extreme properties of materials and especially as they exist in the far reaches of our universe. So, this is about me. Uh, let me just do one thing. Give me a second. I think people have to get admitted to join. So what I'll do is I'll just enable everyone to join just like that. So, okay, give me a second. Let me just change the meeting settings, I think. Mm, settings. Just give me a second because then I don't have to admit people. Okay. Hmm. What is here? Okay, controls maybe. So enable lobby. I'm just removing a few more options. Meeting access. Who can bypass? Who can admit? Okay, fine. I think now everyone can just join without going through the lobby. Okay, anyway, I'll make sure that's the case. Anyway, as I was saying, this is about me. So what are these sessions for? So you already have the lectures videos every week that hopefully you've been watching and keeping up with, and those will be released on a weekly basis. Along with that, every week you have this assignment that you have to solve, which goes through towards your certificate and other things. So these are going to be live sessions with me, and I'm going to be kind of recapping whatever is said in the videos. So nothing that you have, and also we are going to solve problems together. The main purpose of this sessions is to make your assignment problems easier. So we are going to solve some problems which are related to your assignment but not exactly your assignment questions. So by solving these problems you'll have a practice for solving your actual assignment problems, and that is the goal of this sessions. So these sessions are basically 2 hours where you can, kind of check in on what's happening, and if you have any doubts, you can clear them with me, and so on. So you already have your recorded lectures, but this is an opportunity for you to get your doubts cleared live, right? So just some bookkeeping things. All these sessions are going to be recorded and uploaded on YouTube. So if you see here, there is a I've made a page on my website. So if you just go to my website, you can find that all these information is given here. So this is the meeting link, the YouTube playlist, and slides of the sessions have not been updated yet because this is the very first session. But once I after this session, I'm going to be uploading the slides in a Google Drive and uploading the video to of the recording to a YouTube playlist, so you can access these sessions whenever you want. Apart from that, this is my mail ID. And apart from this session, if from the next week onwards, if you want me to cover something specific that was taken that week that you didn't understand, or you have some particular problems for me to solve, then you can just shoot me a mail at my ID and I'll try to incorporate that into the next week's session. So essentially, this 2 hours every week, every Monday, is for your benefit, where you can kind of, although you have the videos already, you're not having any, this is a platform where you can actually interact. This is made for being more of an interactive session so that you can live clear your doubts. So this is the idea behind these sessions. It's to supplement whatever videos you're already watching, and so that we can solve some problems together which are related to your assignment problems, so that you can understand your lectures better and you can get better at solving your assignment problems also. So this is the goal of these sessions. So I'm just going to copy paste this website. Sorry. Um, I'll just copy paste this in the chat. Just save this and I'll uh okay, is my voice okay? I just saw the chat that someone said my voice was breaking. Uh is it okay now? Okay,
Yes, ma'am.
fine. Yeah, okay, cool. Thanks. So I'm just copy pasting this website. So just bookmark this or whatever. So all the links are there in the website in one place. So it's easy for you to access. Apart from that, I'll also copy paste my email ID, so that, as I said, these sessions are meant to be interactive. So if you have a particular topic that you feel like wasn't covered enough in the lectures, or you just have some doubts, just send me a mail I'll just try to put that topic in the next session because it may be that many people are having the same kind of doubt, so that it will be useful for everyone. Apart from that, also, if you have any, you want me to solve XYZ problem, just send it to me. I'll try to incorporate it. Of course, please don't send it in the last moment. So these sessions are on Monday. So by Friday of the week, if you send me something, I'll be able to incorporate it into the slides. If you send it later than that, it's going to be difficult. So that's the idea. Okay. So basically, this is the idea behind these sessions every Monday at this time, 6 to 8, unless there is something, in which case the team will inform you. But this is going to be our schedule for the next 12 weeks. Okay. So this is the idea. Uh, so any doubts at this point? I don't think so, because it's just an introduction. The other thing is that I just want to clarify this now, because I've taken these kinds of sessions before, and a lot of the same questions come up. I am not an NPTEL TA, so I am not in charge of correcting your assignments or the exam or those kinds of things. Those kinds of things are directly managed by the NPTEL team. So if you have those kinds of logistic problem questions, like what's going to be the exam date, or how to register, that I can't help you, but I can help you with all the physics of it, right? All the course content, I am here to help you. So that's just a clarification I wanted to make right away. Okay, fine. So, before we start, I just wanted to get an idea of, let me just minimize this again. I just wanted to get an idea of what everyone's background is. Are you all from like a master's level, or doing a PhD, or how is the thing? Or you can either speak or you can put it in the chat. MSc first year. Okay. Okay, faculty. Okay. Okay, PhD second year, MSc first year. Okay, okay. Finished MSc. Okay, there's some people who are also still in BSc last year and so on. Okay, cool. Fine, fine. So roughly you're at, okay, I can see there are a few faculty. I just wanted to know the minimum level. So it seems like people are at least at BSc last year. Okay. So if at any point I use any terms that you don't understand, especially telling the people who are still doing BSc and stuff, please feel free to stop me and interrupt me. Others, I think I won't be using anything that's not been used in the video lectures. So if you're able to follow the video lectures, you will be able to follow my teaching as well. But I just wanted to make sure for the rest of the weeks what kind of level we are dealing with. Okay, great. So, so let's go to the session. So as I said, these sessions are going to do two things. One is to recap the week's lectures. I'll also solve some problems or assignment questions similar to what you're getting in your assignments. And finally, we'll also do some, I'll try to incorporate some extra derivations or extra things that from the course, so that related to the course, so that you get some value of it. So just to reiterate, you can find the everything about these sessions on my page, and you can also mail me. Also, if you go to the course, you'll see something called problem solving session. So here you can see week one, and then your assignment and other things. So this is all the you have to submit your assignment. But if you go to this problem solving session, you will find where to find my recordings and other things. But I think just save my website page. That will give you everything. Okay, okay, that's enough bookkeeping. So I'll just go to the session now. Again, feel free to stop me at any point if you have any doubts, or put it in the chat. I will just join on my phone so I can monitor the chat while I am teaching. Yeah, I'm just on my phone as well. Okay, fine. So just to recap, what's the first week lectures? So again, this is just the introductory week. So the lectures were mainly about introducing this subject of particle physics to you, and looking at particularly Noether's theorem, and we'll be looking at Noether's theorem in some more detail today. I'll try to show you a quick derivation of it so that you can understand where it comes from. Apart from that, you also looked at the scales of the standard model, in the sense that the standard model is really for, everything except gravity, right? We work for everything that is at atomic scale or maybe lower. So we have the gut scale, we have the electroweak scale, and then we have weak interaction scale. And these all, whenever I say a scale in the standard model, that corresponds to, of course, an energy of the energy as well. And we saw how different energies correspond to different processes that are happening. So this is something very important in particle physics, where we have to recognize that certain processes happen at certain energies and with certain lifetimes, or lengths, associated characteristic lengths or characteristic lifetimes associated with them. So we have to understand that when given a time period, what process is dominating at what time. And this is a very important thing that you will be seeing as you go through this course as well. Apart from that, you started looking at particularly parity, little bit of charge conjugation, but mostly about parity. I think you will be seeing more about charge conjugation in the following week. So because it's an introductory, because it's the very first problem solving question class, and you're just off your first week lectures, I wanted to keep the slides fairly basic. So it's important to note that the subject of physics, especially those of you who are doing a bachelor's or whatever, you should know that physics is not about finding the truth of the universe. A lot of us come into physics because we have this idea that physics is going to be about, discovering all the secrets and the mysteries that are there in the universe. And that's why, myself included, when I started a BSc, that's kind of the image I had of being a physicist, right? But that's not true. Physics is more about model building, right? For example, if you look at the models of the atom, of course, we have the plum pudding model, we have the Rutherford model, Bohr model, and probably some insane models that were there in between that have been forgotten. But the point is that, what you do in physics is you see the world around you, you try to build a model that describes that, right? And you try to, and the way that we validate our models, or if we check if our model is actually the correct one or not, is that we try to test it using experiments. That's why experiments and theory are both very important. Theory is what builds the model, experiment is what gives us the proof or the validation of that given model. So there are many models in physics that have been, have been studied, that I'm sure you're familiar with. One of the most famous examples is gravity, right? Newton had this universal law of gravitation, a model for how the Earth goes around the sun and how objects attract each other, that worked so very well and described almost a lot of things in our solar system. But then, when it came to the 1900s, Einstein realized that this model was lacking, and that's what made us to update our model to that of general relativity, which better explain things like black holes and other things. So you can see that in the light of, discrepancies, we may have to update our models, right? So Newton's laws were a good model, but they didn't explain a few things, and we had to update our model to GR. And it's possible that, tomorrow we might discover something that is lacking in GR, in which case we'll have to, update that model further. So this is the idea you have to have when you think about physics. It's about model building. uh, and one of the most successful models in all of physics is that of the standard model. Okay, and I've seen many people, many physicists say that this is arguably the most successful model in all of physics. And you can watch a nice video by David Tong here who talks about the standard model. But this is basically what you will be studying throughout this course. You can see that we have quarks, which are the hadrons, we have the leptons, we have the gauge bosons and the scalar bosons. And this is basically what makes up everything in the universe, arguably, minus gravity, of course. Right? Minus gravity, minus dark matter, minus a few things. But this makes up a lot of what we understand. And whatever this model has been extremely successful in describing a lot of processes that we see around us. Okay, so there are a few things which are missing, but for what it is, it has described a lot of processes extremely well. So you will be understanding more as the classes go on, as the weeks go on what exactly these different objects are. What is the difference between a fermion and a boson, for example? For example, we have these quarks which are in a different color than the leptons. Quarks are hadrons; they interact with the strong force, whereas leptons don't. And all of this is encoded in terms of symmetries, which is what you started looking at in terms of in this week's sessions. You learned about symmetries and all that, and those are very important because the behavior of each species of particle depends on what underlying symmetry it obeys, right? Each force in the standard model also depends on what kind of symmetry or what kind of, yeah, symmetry it is falling under. So this is the idea behind the standard model. So just keep this picture in mind. Even if you don't fully understand everything that's on the screen right now, it's fine. The goal of these 12-week course is that by the end of the 12 weeks, you will be able to actually identify what this means. Okay. Okay, so the standard model, of course, it describes the fundamental building blocks of all the particles that we see, and the interactions between the particles can be described in terms of the fundamental forces. So these are the fundamental forces arranged in terms of their relative strengths. So that means that if I give the strong force a strength of 1, then how much is the electromagnetic in terms of the strong force? It's 1 by 137th the strength. You can see the weak force, true to its name, is only 10 to the power minus 6 times the strong force, whereas gravity is a really, really weak force. And this is also why gravity it's okay that, for the model, for the processes that we look at in high energy particle physics or in the standard model scales, it's okay to ignore gravity because gravity is so weak when we compare to the other processes. But why is gravity still important? Because as you can see, the strong and weak forces are very short range forces, whereas it's electromagnetism and gravity which are actually the long range forces, right? They have infinite range in practice, right? Even then, gravity can have, in principle, an even longer range than the electromagnetic range, right? Can anyone think of why that is? Let me try to say that again. So we have these different forces like strong force, weak force, electromagnetic, and gravitational force. You can see their strengths in this way. And I'm just saying that in terms of the standard model, you can see that, at the processes at high energies, it may be that gravity does not play a role because its strength is so weak when compared to the other forces. But at the same time, gravity cannot be ignored all the time, right? Even when the strong and weak forces die out at large distances, gravity and electromagnetism may still survive. But I'm saying that gravity can survive even when electromagnetism can't. So can you think why? Okay, I have to exit out of this to go to. So someone had raised their hand. Go ahead.
Ma'am, perhaps because gravity is dependent on mass and mass can clump together and it can become more and more massive. But charge, we don't really see charges clumping together. So in that analogy, gravity exists in large scale because the potential is dependent on mass.
Yes, yes, that's true. But so I think you are like 70% there. So it's very true what you said, which is that gravity can always be increased because you can always have masses clumping together, whereas in an electromagnetism you can't. So the reason for that, why does mass clump together, why charge does not? Because the interesting thing is that gravity is only an attractive force, right? Whereas electromagnetism, because you can both have positive and negative charge, electromagnetism can be both positive and negative. So if you bring a lot of charges together, you can't just bring like charges together, first of all. On the other hand, if I bring a lot of unlike charges together, they're just going to cancel each other out, right? So that's why, and we know that that's a good thing because everything is electrically neutral. Because of that, atoms are stable because positive and negative charges can kind of cancel each other out. So the answer to that is because there is no sense of kind of a negative mass I only have attractive forces of gravity. So gravity can in principle be an infinite range force. Whereas electromagnetism, even though in principle it's also an infinite range force, in practice, because we have two different charges, because we have attractive and repulsive forces which can cancel each other, this is not always realized. So gravity is, just I'm just trying to put it in your head that gravity is a little different when you compare to the other forces. First of all, its range is much higher, and second of all, its strength is much lower. We still, you can see that every force is also associated with a particle, and that is the particle that we exactly see in terms of the standard model. So these gauge bosons, which are called the vector bosons, are actually the force carriers, as they are called, because they are responsible for the different fundamental forces. So for example, the gluon is the force carrier of the strong force. The photon, of course, is the force carrier of electromagnetism. And you have the W and Z bosons, which are the force carriers of the weak force. We still don't know what the force carrier of the of gravity is. It may be something called the graviton, but that's still theorized. We don't have a good theory for it. We don't know how it acts, and we don't have a place for it in the standard model. People can predict some of its properties, but we still don't have it in the standard model. But yeah, people try to come up with some theories for it. So this is the idea of the standard model. It deals with these particles and these gauge bosons. These gauge bosons are responsible for the first three forces that you see here. And with, these particles can interact with each other, they, using these gauge bosons, and that all together gives us an idea of how different processes can take place, right? So this is the idea behind the standard model. So yeah, again, so this is just about the standard four fundamental forces. So, right, so this is the standard model. Now, of course, the particles which you see here, they don't just, exist like this. Of course, the point of the standard model is that the matter particles can are building blocks to form other particles, right? For example, you know that the up and down quarks can combine together to form protons and neutrons, and that's eventually what leads to all the atomic matter that we see around us. That's what makes us up, for example. And you can have different combinations of these particles as long as they obey certain, charge conservation and so on, so that you can actually get different kinds of particles. So usually these particles are seen, can be represented in terms of this kind of octet or nonet, eightfold way it's called, where you can form different kinds of particles. So for example, from the quarks itself, you can form all the baryons and the mesons. So if you have two quarks joining together, that's called a baryon, whereas, sorry, yeah, two quarks joining together, that is a quark and an anti-quark, that is a meson, I'm very sorry, whereas three quarks joining together is a baryon. Again, you will learn all this in more detail. How exactly we can join the two quarks or the three quarks together is very important. Another thing is that when I showed you this picture, this is not a complete picture. For example, when I spoke about meson, I said that a quark and an anti-quark join together. So it's important to note that for all the matter particles that I show here, they all have their corresponding antiparticles as well. So there's an, anti-electron, which is sometimes called a positron. We have, usually antiparticles are denoted with a bar on top. So I'm just saying that all of these particles also have their corresponding antiparticles. So again, you'll be learning about all these things, about antiparticles, about how to put particles together to form baryons and mesons. You'll be learning about all this in the course, so don't worry. I'm just trying to introduce a bunch of terms to you so that later when you come across them, you have some context for where they come from. Okay, so for example, you can see spin half baryons, spin zero mesons, spin one mesons, and spin three half baryons. So you can see that the mesons are made of, one quark and one anti-quark, whereas the baryons are made of three quarks, and this is how you get it. And of course, the most important baryons for us at least are the neutron and the proton. The neutron is made of two down quarks and an up quark, whereas the proton is made of two up quarks and a down quark. And again, you'll learn about why this is and how it makes sense later. So We have particles and forces at different energy scales, that is different lifetimes, which we just saw in the previous slide as well, which is that different processes in the standard model, or the different fundamental forces, actually have different relative strengths and and thus and different ranges over which they are active. So this is kind of a theme that you have to keep in mind. That's what I started the video with as well, which is that, in particle physics, it's important to know the energy scales of different things, because we need to know what process dominates over other processes. For example, if two processes are happening at the same time, but one takes years to happen, whereas the other is of a time scale of 15 minutes, it depends on what time scale you're seeing, right? So for example, because I am an astrophysicist, in the sun, for example, you have processes that take millions of years to happen, like, billions of years to happen, like the nuclear fusion. But you also have, processes which are taking 15 minutes, like these small eruptions and things like that. So if you're looking for a time scale of a day, it's going to be those eruptions and ejections which are dominating. Whereas if I look over the age of the universe, it's going to be the nuclear reactions which are important. And there are similar lifetimes associated with particle physics processes as well. So that's why it's important to know that what is the force that's happening, what's the lifetime, what's the length scale over which it is active. So finally, this week you saw what was parity. So parity is the first sort of symmetry of the standard model that you came across. Now, symmetries are very important because symmetry is kind of like the grammar of the standard model. So you write a language, it has a grammar, it has a syntax, right? So in standard model, the I would say the language is in terms of group theory, which is a mathematical thing. Again, you'll be learning this as you go along. And the grammar of each, the kind of the funda behind each of the forces and how they interact is given by what symmetry they obey. And this is exactly the first symmetry that you saw, which is a discrete symmetry, which means that it's not a continuous symmetry. And you will be seeing continuous symmetries later, which is that we just go from x to minus x, y to minus y, z to minus z. That's what's called parity. Essentially, we're just it's like an inversion, right? And based on how quantity behaves under parity, we can actually classify it into different categories. So here you can see that I've given a few examples. So you have scalar, pseudoscalar, vector, and pseudovector. So you know that you will be familiar with scalars and vectors. You know that scalars are basically invariant quantities, just magnitudes, just amounts of things, right? Like mass or temperature. And it's understandable to think that if I invert the coordinate system, the mass of an object is not going to change, right? If I weigh 10 kg, even if I put the object at minus x, the object is still going to weigh 10 kg. Or if it's 10 degrees Celsius, it's still going to weigh 10 degrees Celsius, right? So that's a scalar quantity and it does not change sign under parity. On the other hand, a vector quantity changes sign. And again, this is easy to understand because you know that a vector is characterized by having a magnitude as well as a direction, right? So it makes sense that if I change the coordinates, then the direction is going to be reversed and that's going to change the sign of my vector. So for example, if I have a displacement of let's say 10 meters in this direction, if I suddenly now change my coordinate system to be the opposite direction, then in essence, I have had my displacement vector is going to have a negative value because my coordinate system has changed, right? So this is the idea behind a vector. The more interesting things are pseudoscalars and pseudovectors, because pseudoscalars are scalars in the sense that they only have magnitudes, but they still change sign under parity. So one example of this is magnetic flux. You can think about why this is by understanding what is a pseudovector first. So pseudovector is a vector which means it has a magnitude and a direction, but it does not change sign even when I reverse the parity. And usually pseudo vectors are made of two vectors such that they are a product of two vectors, like say torque is r cross f, right? So that means that when I change the coordinate system, both r and f obtain a negative sign, so that overall I get a positive sign. Another very famous example of this is the magnetic field, because magnetic field by your Lorentz force law is nothing but q V cross B, and when V and B both change sign under parity, overall the magnetic field is going to have a positive sign. So now you can understand what pseudo scalars are. It's the same concept where it looks like a scalar and we expect it to change sign. We expect it to not change sign under parity, but it ends up changing sign. So magnetic flux is one such quantity because it's the dot product of B and A. B dot A is the magnetic flux, whereas B does not change sign under parity. A, which is the area vector, does change sign under parity, being a normal vector, and so all together you obtain a change of sign. So whenever you see this pseudo scalar or pseudo vector, it just means that it has a behavior which is opposite to what we conventionally expect from these objects. Okay. So this is about parity, just to give you an idea of how parity can impact things. But of course, we are talking about particle physics. Particles can have their own parity. For example, you saw that parity of a photon is -1, parity of a quark is 1, and this is a convention, right? That makes the antiquark to have a parity of -1 and so on. So this is just how you think about parity in terms of particles. It's like a convention just to think about what does this particle behave like a scalar, a vector, or so on. And this is again relevant because we are going to be later describing these particles in terms of mathematical objects. And it's very important for us to understand what type of mathematical object the particle maps to. Does this particle map to a scalar? Does it map to a vector? And so on. So again, don't worry if that kind of goes over your head right now. It's going to be clear in the very much upcoming lectures. One very interesting thing, even at this stage, that you can appreciate is that neutrinos do not have any parity eigenstates. One very interesting thing is that you also learned a little bit about helicity this week, is that there are no right-handed neutrinos in the standard model. So that means that left-handed neutrinos do not have a parity partner, and so in essence they don't have reflection. So essentially neutrinos are like vampires where they look in the mirror and there is no reflection. And this is because neutrinos mostly come through the weak interaction. And as you saw this week, weak interactions usually are parity violating processes. So that's a very interesting thing to keep in your mind. There's a short video about it that I've linked in the slides that you can go and watch. Okay, so that brings me to the recap, end of the recap. So again, just to reiterate, I'm going to be doing this in the classes where I'll just recap a few of the points that were done in the lectures. I won't be doing the lectures again because you already have like 4 or 5 40-minute videos to watch. So I'm just giving you just the highlights of what was discussed that week. If you want me to cover something in more depth or more detail, maybe you watch the video and it's not clear to you, don't forget to just mail me on like within the week, then I'll try to include it in my next week's lecture, for example. Okay, for now, let's go to the next part of the session, which is about solving some questions. So I'm going to show you the question. And since this is an interactive session, I'm just not going to show you the question and give you the answer because I think that's boring. So I'm going to show you the question. And I think there are, only a few of you, there's like 10 or 11 of you. I want all of you to like just put your answers in the chat and then we can try to see if you guys get it right. And again, this will be good practice for you while you try to solve your assignment questions as well. Okay, so please, everyone, please respond in the chat. Again, the reason behind this interactive sessions. Okay, fine. So, first question, up, charm, and strange are, there are four options. Please put your answers in the chat. Okay, someone says the three colors of quarks. Okay, looks like B is the one that everyone's going for. One person says C. Okay, I think four people say C, three people say B. Any other answers? Anyone else? I'll give you a minute to answer in the chat. Okay, someone says D. Okay, okay, now I can see other answers as well. D, C. Okay, I think the majority has everyone answered. Please, everyone answer. There's only 10 people. I think everyone can answer. But yeah, I think so far the majority seems to be C, with few people saying B and D. So let's go to the answer. The answer is actually three flavors. Okay, so the important thing to understand here is that, okay, so when I look at quarks, there are a lot of different things to understand about quarks. Okay, first of all of these are flavors of quarks. Okay, up, charm, top, down, strange, bottom. They are all called quark flavors. Okay, so at the same time, so one very funny thing is that the physicist Murray Gell-Mann, who actually came up with this name of quark flavors and other things, actually came up with this idea because he used to go to an ice cream shop and he saw all the different flavors of ice cream, and that's actually what inspired him to call quarks of different types as flavors. So that's a very interesting tidbit. It's completely true. He went to, I think, Baskin Robbins or something. Anyway, so each quark flavor is like based on, it has a different mass, it has a different charge, spin, etc., as you can see, right? So that's a quark flavor. And every flavor has, the corresponding anti-quark also. So there's up and then there's an anti-up quark and so on. Now, the generations of quarks are this one, two, three, which is given here, right? So up and down form one generation, charm and strange form one generation, top and bottom form another generation of quarks. Okay, so that's like they're kind of, you can see that up and down have similar masses, charm and strange have similar masses, and top and bottom have similar masses. So those are what are called the generations. Apart from all this, when you characterize a quark, apart from mass, charge, and spin, you usually use another quantum number. And again, the reason for this you'll understand, you'll be learning in the lectures soon. But you usually use a third quantum number, which is called the color. Okay, so every up quark, it can be a red up quark, it can be a green up quark, or it can be a blue up quark. There are three colors of quarks. Okay, so remember, the three generations of quarks have nothing to do with the three colors of quarks, right? The three colors are for each quark flavor itself. So up itself can have color red, green, or blue. Charm can have color red, green, or blue, etc. So that's the understanding that's here. Okay, so that's not to do with this. Okay, so that's the kind of, because there are so many quantum numbers, it can be difficult to understand, but this is the terminology. So in the question, actually, it's a kind of a sneaky question because I asked up, charm, and stage. If this was up, charm, and top, then I could say, yeah, these are three different generations of quarks. But charm and strange are actually from the same generation only. Up and down are the same generation, charm and strange are the same generation, top and bottom are the same generation. So this is actually just three flavors of quarks. Okay, so that's why D is the correct answer. Is this clear to everyone? Any doubts? Okay, good. If you have any doubts, just stop me whenever. Okay, great.
Excuse me.
Yeah, yeah,
Ma'am,
sure.
can you
Go ahead.
please restate what do you mean by color of quarks? Generation was
Okay,
clear. Color of the
yeah.
quarks.
So color, for now, just think of color as an additional quantum number. So you know that okay, a quantum number, don't even think of quantum number. Think of color as a property, right? Like every quark can have a charge, right? Like that quarks can also have color. Okay, it's just a property of them. Why you need this property, you'll understand later when we put quarks together, like baryons and mesons. That time you realize that in order to, you need an extra quantum number to describe them, basically. So that's just how it is. You'll understand the symmetry behind color and all that. Just think of it as an extra, like quark has a mass, quark has a charge, and quark has a spin, quark also has a color. And this color can be three things. They are usually called red, green, and blue. It's just some arbitrary name. This has nothing to do with actual electromagnetic light or the color that we see or anything like that. It has nothing to do with that. It's just a name. Okay. Just like up and down doesn't mean the quark is literally up or down. It's just some name that was given by someone and that we follow. Is that clear?
Yes, ma'am.
Okay, good. So yeah, you'll be again, you'll the reason I'm not going into too much detail about these things is you have 12 weeks, so you'll be figuring these out soon enough. But just to know these terminology is good. Okay, next question. Under Lorentz boosts, Noether's theorem implies a conservation of the for which of the following? So again, please put your answers in the chat. Okay, two people say A. Okay, seems like many people are saying A. Okay, can see that's B, B, A, A, B, A. Anyone left to answer? Okay, someone says D. Uh, okay, I'll give a minute in case someone's answering. Okay. If not, we can go to the answer. So the answer is actually the center of mass position. I think few of you did answer this. Most of you seem to go for A. So space-time interval is a conserved quantity. ds squared is equal to, time coordinate square minus position coordinate square. But that is not because of Lorentz boost, right? So no, neither's theorem is not just about conservation. Neither's theorem is about um, associating conserved quantities with symmetries. So, for example, time translation symmetry leads to conservation of energy, position translation, translation in position space, if that's symmetric, that leads to conservation of linear momentum, and so on. So, this is a little more difficult to see. We'll see a derivation of Noether's theorem after the questions if I have time. But this is basically based on a continuous version of Noether's theorem, and there's a nice discussion of it in this web page. So I've just linked it in the slides. You can go through it. So, for example, you can actually get an intuition for this by thinking of, Galilean transformation. So, Galilei, before we had, an idea that, actually special relativity implies the speed of light is constant, and we have this Minkowski space. Before that, the way that people thought of relativity is through Galilean transforms. And from that itself, you can see how, just having symmetry in that case leads to a conservation of this mass position, because basically you go from x to something like x plus vt, And then, you already know that transforming x gives you linear momentum, and from that you can kind of figure out the center of mass position. So there's a very quick derivation of it here. For example, you can see that t goes to t, x goes to x plus vt, y goes to y, z goes to z. This is basically a Galilean transform. And then, because x is going to x plus vt, p goes to p plus mv, for example. And a Galili boost is just a translation in momentum space. So from that, you can get the center of mass coordinate is transformed, and that is seen here. Okay. So I would say try to work this out. It's not, I'll show you a derivation of the general Noether's theorem after the questions, and that should help with this, because this is like basically a generalized form of that. Okay. So I'll just go to the next question now. If you have any doubts, can let me know, but I'm just going to go to the next question now. Next question is the gluon is A, B, C, or D. I think I discussed this just now. Okay. Okay, good. Everyone's answering immediately. Okay, I think we can go to the answer. The answer, as all of you got it, is that the gluon is actually the force carrier of the strong force. So again, just going back to a few slides ago, in this slide, you can see that every force has an associated particle, which is the carrier of that force. So with the strong force, it's gluons. Ignore the pi for now, you'll understand later. For electromagnetic, it's the photon. For weak, it's the W and Z vector bosons. And then for gravity, maybe it's the graviton, but again, because we don't have a good handle on how to incorporate gravity into the standard model, the particle kind of nature of gravity is still not very well established. But these three are very much established, and that is what is the answer. Okay, good. All of you got that. Next question. Which particle state is stable because it's the lightest fermion? Okay, people are giving two options. There's only one answer. Okay, I think almost all the options are there in the answer. I don't see a clear majority yet. Everyone, please answer. Then we can try to see if we can get a majority. So read the question carefully. Which particle state is stable because it is the lightest fermion? Okay, so there are two words there. Okay, okay. I can see the same people are answering. Okay, okay, good. Yeah, but the question is not about the lightest charged fermion. It's just about the lightest fermion, right? I think I'm giving things away, so I'm just going to go to the answer. I think you guys have had enough time. The answer is C. So I think some of you, so first of all, if you just look at these particles, which is the lightest, of course, it's the photon, because technically photons are massless, right? But of course, the answer is not photon because photons are not fermions. Photons are bosons. In fact, we know that photons are vector bosons because the photon is the force carrier. So remember that all force carriers are bosons. Okay, so photons are bosons, gluons are bosons, and W and Z are also bosons. Okay, fermions only make up matter. That's the first thing. Okay. So now electron, proton, or neutrino, right? We know it's not proton because proton is not the lightest fermion because proton is a composite particle. It's made up of other things. So definitely it can't be the lightest. And we know proton is like 2000 times the mass of the electron. So it has to be electron or neutrino. So the answer is a neutrino. In fact, even though the electron is only like, what is it, 500 keV, still the neutrino is even less. In fact, the neutrino is very close to massless. Okay, and in fact, in the standard model, the neutrino is actually massless. You can see that it has a very small mass. The reason behind the neutrinos having mass here is very interesting, and you'll be learning it in the course. But in technically, neutrino can be thought of almost like massless particles. So that's why the answer is the neutrino. Again, the question didn't say charged under U1 or anything like that. So the question was just which is the lightest fermion, and that's the neutrino. Neutrino oscillates, yes, because of mass. That's why I didn't want to go into that right now. But that's why. In the standard model, however, neutrino does not oscillate. If you just take the standard model, neutrino is technically supposed to be massless. Sorry, yeah, but because of neutrino oscillations, they have a very small mass. Just because of the mass eigenstates. Okay, good question. That is still stable because it's not decaying into another particle, right? The way that it oscillates. So, okay, for those of you who don't know, don't worry about it. I'm sure it'll be covered in the course. But neutrino can oscillate from one flavor to another. So, an electron neutrino can become a muon neutrino and so on. That's still a stable process. Here we are looking for more of like, decay. Like, for example, a neutron, if you just have a free neutron, that decays immediately, right? Because you have two lighter particles that it can decay into. Neutrino does not have that. If you have just a free neutrino, it does not decay like that. Okay, so that's the idea. The neutrino oscillation comes a little differently. It's a very good question, but that's not the context here. Okay, don't worry, we'll discuss it later, I'm sure, in the course. But apart from that, is this fine with everyone? This question is okay. Any other doubts? Okay, good. So one important thing to remember, and we can talk about this more later because I work with a lot of fermion bosons and quantum statistics. But one thing to kind of remember at this moment of like fermions make up matter, whereas bosons are the force carriers. Okay, so you have to always have this in mind. Photon is a boson because it's a force carrier. Electron makes up matter, it's a fermion. So it's very important or it's very good that matter is made of fermions, right? Because you might know that fermions obey the Pauli exclusion principle. Okay, and that's a very important thing about them. It's related to something called the spin statistics theorem, which you'll be seeing in future weeks. But what that means is that you can't just put in so many fermions together, right? And that's why, we can have stable structures because fermions cannot be just smooshed together arbitrarily. So matter can exist, atoms can exist, whereas bosons will just all condensate together into the ground state, and you can't really have excited states and all that and form atoms. Okay, so that's why fermions form matter and bosons carry the forces. So that's how you have to remember this. So, if you have like, one day you might have a doubt, was photon a boson or a fermion? Just remember that force carriers are always bosons. Okay. So this question, I think few of you answered already, but which particle state is stable because it's the lightest electrically charged one? Okay. People are saying A. Okay. A, and I can see few people saying B, which is proton. Okay, is there anyone else left to answer? Otherwise, I can go to the answer. Sorry, is there a question? Okay. If you have a question, by the way, stop me at any time. Okay. These are interactive sessions, so feel free to, interact. Okay, let's go to the answer. The answer is, of course, electron. I don't know. I maybe some of you got little confused because you were saying proton. Remember that protons are 2000 times heavier than electrons. Okay. So proton is like I think it's like 1830 or something, 1836 times the mass of the electron. Atoms masses come almost entirely from the protons and neutrons, right? When we say atomic mass, in the periodic table, when you find out the atomic mass of each element, that's based on how many protons and neutrons there are, because those are the massive particles and the electrons are almost, you can neglect them. Okay, so remember that protons are much, much heavier than electrons, 2000 times, like three orders of magnitude. Okay, and of course, electrons, the answer here is not neutrino because neutrinos are charged less. So here we are looking for charged particle, or as someone had said that, under U1, electron is the, lightest particle which is charged. Again, if you don't understand that, don't worry. Okay, is this clear to everyone? Can't be photon because photon is not, and then neutrino is also not. Okay, electrically charged. Okay, so I think I also spoke about this, unfortunately, but yeah, can neutrons decay? Put your answers in the chat. Okay, again, I can see split between A and B. Okay, someone says C. Okay, maybe we can go to the answer. So I think the majority of you got this correct. The neutrons can decay if they are not bound in nuclei. When neutrons are in nuclei, they are stabilized by the strong force. But if you cannot have a free neutron, it will immediately decay. Does anyone know what it will decay into? When a neutron decays, does anyone know what it decays into? Aha, proton. Nothing else, just a proton. Yeah, it can't just be a proton, right? There has to be at least proton, electron, and also something else actually. Neutrino, exactly. So a neutron decays to a proton, electron, and a neutrino. Do you guys know what this process is called? Actually, an anti-neutrino. What do you know what this? Yeah, not a neutrino, anti-neutrino. My bad. You guys know what this process is called? Yeah, this is one of the beta reactions, right? So you might have learnt about this alpha beta reactions, right? So beta reaction is basically this neutron decays into proton, electron, and antineutrino. So why is it electron and antineutrino? Because both of them have, one has a positive lepton number, other has negative lepton number. So the lepton number is conserved, and there's one baryon on this side, which is a neutron, one baryon on this side. So baryon number is also conserved, and then proton has charge 1, and then electron has charge -1, so charge is also conserved. So these are the different things you have to check to see if a reaction is possible, right? First of all, the mass on this side has to be greater than the mass on the other side. Otherwise it won't decay, right, in the first place. So neutron is actually slightly heavier than the proton, which is why this happens. And the inverse reaction, proton doesn't decay into neutron, right? Proton plus electron can form neutron. That's called inverse beta decay. But proton doesn't just give neutron like that. So it has to be with some energy. So yes, so proton, electron, antineutrino. So again, you can check, is charge conserved on both sides? Is charge same on both sides? Is the baryon number same on both sides? Is the lepton number same on both sides? These are all things you can check. So this is beta decay. In fact, beta decay is how Fermi actually discovered or proposed the existence of the fermion, which is named after him, because we realized that in beta decay, there was a small part of energy that was not accounted for, and eventually it was found that, there is actually another particle also that we have to take into account. Okay, next question. Parity is conserved in. Okay, okay, sorry. Hmm. Mm, open my phone. Okay, I can see again multiple answers. D, C, B, and then again C. Okay, B. Hmm, okay. Maybe we can go to the answer. So the answer is actually gravity and the strong force. Okay. So first of all, I think already in the lectures you saw that the weak force violates parity, right? The weak force does not conserve the handedness. And this is a very important discovery about parity violation of the weak force. So we know that weak force cannot actually conserve parity. Electromagnetism also cannot, because you can always have particles, where you have, for example, positive and negative particles which are interacting, and that always violates gravity. Okay, so but definitely, no, electromagnetism. Okay, let me think about this. Does electromagnetism conserve parity? Well, okay. Yeah. Electromagnetism does conserve parity. Sorry. I was talking about charge. Electromagnetism does conserve parity, but the weak force does not. The weak force out of all the four forces does not conserve parity. So that's why this option is wrong. This option is obviously wrong. Here, electromagnetism and gravity both conserve parity, but this option also says, but not in other forces, which is wrong, because a strong force also conserves parity. So that's why C is the correct option. Okay, sorry about that. I for a second got confused with charge and parity. Does this make sense? Okay, the parity is all violated in the weak force. Okay, so that's why D is not the correct option. Obviously, A is also not the correct option. B looks like it may be correct, but it says but not in other forces, and that is wrong. That's why C is the correct answer. Okay, this is clear to everyone. So always read all your options properly. Like read the entire option. They try to trick you in these things. Don't fall for it. Okay. Good. Is it just because neutrino in weak force that causes? Yeah. Partly yes. Because neutrino, as I said, does not have a right-handed partner, right? So we cannot get this parity violation, parity conservation. But yeah, you will also see from the symmetry why it's the case. I'm sure you will see in the upcoming lectures. Okay, next question. The intrinsic parity of a meson is blank. A, someone says B. B. Okay, okay, everyone says B so far. Okay, B. Okay, okay, I think we can go to the answer. Good, I think you all got this. Minus 1 to the power of L plus 1. So can anyone explain why L plus 1? Fermion antifermion pair, sure. So what?
Mesons has intrinsic angular momentum. So meson has also a bound state.
Yes, yes, correct. So meson has some it may have an intrinsic angular momentum which comes from, yeah, being part of a fermion and antifermion. So a fermion antifermion pair has a parity of 1. This you saw. And on top of that, it may have some other angular like a orbital, or whatever the other angular momentum number L. So altogether you have L plus 1, which is coming from the bound state of the fermion antifermion pair. Okay, very good. Cool. Next question. In the decay pi plus, this is a meson which is going to mu plus, this is like muon and the neutrino mu. Sorry, it's not, I didn't latex it. Neutrino muon. Sorry, muon neutrino. The helicities of the final products in the pion rest frame are. Okay, I can see D, C, D, A, C, C. I'll give one more minute in case people are still answering. Okay. Okay, we can go to the answer. The answer is actually equal. Does anyone want to try explaining why this should be? So there's an interesting process. It's called helicity suppression. Why should the helicities be equal? First of all, helicity means whether a particle is left-handed or right-handed, right? Right, spin and momentum conservation, exactly. So we already know from our, classical physics that when you have a collision or something like that, the momentum has to be conserved, right? So obviously these two particles will have opposite momenta. So because the momenta are, opposite, and the spins have to be because of the conservation of angular momentum, the spins also have to be opposite. So altogether, that means that both of the helicities have to be equal. Okay, and you can again take the definition of helicity and you can see why this is. So again, just because of the constraint that the momenta are equal and the angular momenta are equal, which makes the spins opposite. Because the spins are opposite, the helicity has to be equal so that it balances out. That's the idea here. From angular momentum conservation, we can get the spin and so on. Okay. Okay, fine. Okay, the next question. Okay, someone says, I think this is a question you guys should answer immediately. Good. So a lot of people have said B. The Okay, okay, good. All of you are saying B. The answer is actually B, Madam Wu. So Yang and Lee were the people who first, theorized that this parity violation could happen in the weak force, in the weak sector. But it was Madam Wu who actually experimentally verified this using cobalt 60 and, checking for its chirality under different processes. Unfortunately, Lee and Yang both got the Nobel Prize, but Wu did not. Even though, all three of them, even though they came up with the theory, it was really her experimental work that actually verified that theory. And remember what I said in the beginning, physics is about model building, and the only way that we figure out if our models are correct or not is through experiments. So that's one of the big, like, uh, cases in physics where the Nobel Prize, was not awarded and people have no idea why. There are few such cases. But yeah, it's usually that when women or, are there, there's a lot of cases of a lot of women who are deserving of the Nobel, Science Nobel in historical or a few, decades ago who did not get it. I see that it's slowly changing. Now, there are at least three Nobel Prizes that have been gone to women. So that's good. But yeah, we have a long way to go. So yeah, this was Madam Wu, again the Cobalt 60 experiment, which again you have discussed in your lectures. Okay. Anyway, so with that we get to the end of the questions. So before we end, we have like 30-40 minutes left. So I just wanted to further go into Noether's theorem because again this is one of the most important results in physics. Again, going from one woman physicist to another, which is nice. But yeah, it's one of the most important results in theoretical physics and mathematics. And also it is very, very important in the context of particle physics because, as I said, the grammar of the standard model really comes down to symmetries, and this is a law that has to do everything to do with symmetry, right? So I just wanted to give a quick derivation of Noether's theorem so that you get, which is not very difficult to understand once you have a few tools in hand, and from this you can actually verify the things that you saw in the lecture, right? That time reversal symmetry leads to energy conservation, that linear displacement, what is it called? Position translation leads to linear momentum conservation, and so on, So you can actually verify it yourself. So I'll give you the general framework of how we can get this theorem. Okay, and I think some of the people, if you are have taken an advanced classical mechanics course, some of these things may be repetitive, but please bear with me, and let's just, if you know this already, we can just at least sort of revise about it. Okay. So, the prerequisite to understand this is Lagrangians. Again, if you've not heard this word before, don't worry, you'll be hearing it a lot in this course. A Lagrangian is basically just a function of the coordinates, velocities, and time of a physical system. And using the Lagrangian, you can always construct a Lagrangian of a system, and from this, you can derive something called the action. Okay, and this is a very interesting thing, and even within the realm of classical mechanics, this gives us a new way to think about how to derive motion, the laws of motion. Okay, so you have this Newtonian way, which we learned from school, where we have Newton's laws of motion, and we have, F is equal to ma kind of thing, and from force balance and free body diagrams, we can get, the motion of, say, a pendulum and all these things. But the Lagrangian is actually a completely, parallel way to solve the same kinds of problems, leading to the same kinds of answers. But it's very useful when you have these, more complicated systems. So again, if you have done, if you're in MSc first year, or something like that, you're probably doing a classical mechanics, advanced classical mechanics course, where you are seeing Lagrangian or Hamiltonian mechanics. If you haven't seen those, don't worry. As I said, Lagrangians are again one of the ways in which we describe a physical system, and they are very important when it comes to field theories, which are what we'll be dealing with when we look at the standard model, for example. So you will be, getting introduced to Lagrangians and seeing more of these later in the course. So don't worry about it for now. The interesting thing about Lagrangian is, as I said, you can lead to an action. And one of the very important laws of physics is that the path that a particle follows, or a system follows, is the one that leads to stationary action, which extremizes the action. So either it leads to a maximum or a minimum in the action. And this is kind of like Fermat's theorem in light propagation, right? Light follows the path of least time, right? And that's another way to think about it. So instead of least time, we want to minimize or maximize the action. So if you actually try to do that, what this leads to, the principle of stationary action, leads to something called the Euler-Lagrange equation. And this is actually the equation that you solve in order to get the particles, motion, and other things. So this is kind of like the F is equal to ma of Lagrangian mechanics, right? So in Newtonian mechanics, you have F is equal to ma. If you plug in all the correct F's and ma's, you get the motion of the system, right? So in Euler Lagrange, or in the Lagrangian framework, you have to kind of plug in these different things, and that's how you get it. Okay, so again, don't worry about how a Lagrangian is constructed. All those things you'll learn later, but this is it. And usually this dou partial derivative of L with xi dot. So basically, by the way, xi is the coordinate, xi dot is the velocity. Here dot just denotes the time derivative, very common notation, and time is t, right? So this basically ddt of dou L by dou V. Xi dot is basically V. And so you can kind of, this is usually defined to be the conjugate momentum to this. Okay, so dp dt is equal to del L. Now, one very interesting thing about Lagrangian mechanics is that, similar to F is equal to ma, F is equal to ma is the same no matter what coordinate frame you're in. Similar, unless you think of like pseudo forces or something like that. But similar to that, here also x could be any coordinate, and then corresponding to whatever x it is, you would get some momentum. So if x is just the translation position in linear space, then the conjugate momentum would just be linear momentum. But if x is like a rotation, if it's an angle, then the conjugate momentum would be angular momentum. Okay, so this is how you think about it. So this is some coordinate, this is the momentum that is conjugate to that coordinate. Okay, that's just how you think about it. I know these are a lot of terms. Don't worry, you will learn this more. Again, if you haven't learned this already, you will be seeing it in more detail in one of your courses. So essentially, this is how the equation looks. Okay, so this is our F is equal to ma. So why is all this important? The most important thing is that the Lagrangian of a physical system is not unique. Okay, if L describes a system or some sort of physics, then L plus some derivative df by dt also describes a similar system or the same physics. Okay, and again you can prove this using the principle of stationary action, because again what matters is that we want to minimize this integral, and if I add a just a derivative kind of some sort of function which is a perfect differential of some other function, then that's just going to give me a constant, and that's not going to matter at all when I eventually extremize my action. That term is just going to disappear. So it all comes down to the fact that what we are actually worried about, or the physical thing that we are actually looking for, is the action of the system, right? The physical quantity we want to care about is the action, and we want to not just take the action, we want to extremize it. We want to find either the maximum or the minimum, and the path that corresponds to this maxima or minima is actually the path that my particle will follow. This is the idea. Okay, so because of this principle of stationary action, that means that Lagrangian is not unique. I can always add some arbitrary function to it. I mean, as long as it's of this form and it describes the same physics. Okay, so now we are going to consider that the Lagrangian is independent of some coordinate xj. Okay, and this is exactly what I mean by a symmetry, right? That means that for a given coordinate xj, if I change xj to say 5xj, or if I change it to 2 plus xj, or xj to the power 4, it doesn't matter. So that's what I mean by the Lagrangian is independent, or it's symmetric under transformation of xj. Okay. Okay, so that's the idea here. We want to describe a symmetry. By symmetry, I mean that the Lagrangian does not directly depend on some coordinate of the system, some coordinate called xj of the system. Then the partial of Lagrangian with respect to xj is 0, because it does not directly explain, go to it. Now, if I look at the Euler-Lagrange equation, which is basically your F is equal to ma when it comes to Lagrangians. If you look at this, you can see that if this term goes to 0, if there's a symmetry, then this right left hand side is just going to be 0, right? I'm just setting the right hand side to 0. So basically I get ddt of del L by del xj dot is equal to 0, and this quantity, as I said, is just the conjugate momentum. So you get that some conserved quantity comes out, right? Because now you see that if the Lagrangian is symmetric under xj, then pj ends up being conserved, because this basically tells you that pj is a constant, right? The derivative of pj with time is 0. So this is basically Neither's theorem. You can see that, apart from the setup, which took me a little bit of time and maybe a little difficult to understand if you haven't seen this thing before, but once you know Lagrangian mechanics, you can see that the Neither's theorem is not even two lines, right? It's just one condition, immediately it falls out. So that's the beauty of it, is that it's such a simple concept, but it's such a powerful idea. And you can also see now that if I now take xj to be linear momentum, this automatically comes out to be, sorry, what am I saying? If I now take xj to be time translation, sorry, if I take xj to be the position, then and if my Lagrangian is independent of what position I'm in, then automatically the linear momentum is conserved. Similarly, if I now take xj to be some sort of rotation, then you can work it out and you can see that the angular momentum ends up being what is in this brackets. Okay, so this is a very exciting thing about Lagrangians and Lagrangian mechanics, is they make these fundamental results like this make pop out very easily. Okay. So as I said, xj is translation, then pj is linear momentum. So for another example, let's introduce something called the Hamiltonian. So again, this is a yet another way to do mechanics. So I already told you that you have Lagrangian mechanics where we don't use F is equal to ma, we use this Euler Lagrange equations. We construct something called a Lagrangian out of the coordinates of the system, and then when we apply them to a very specific equation called the Euler Lagrange equation, all the equations of motion fall out, right? Another way to do the same thing is to look at Hamiltonians. Okay, so Hamiltonian is another derived quantity where it's actually related to the Lagrangian. You construct it out of, conjugate momenta and xi, and you can see that this is the form that it takes. If I now take the time derivative on both sides, you can see that so this will be pi dot xi dot plus pi dot pi xi double dot. This is the chain rule minus dl dt. Okay, and dl dt you can take it to be this. Again, this is because L depends on xi dot and t, so you can just expand it. Again, this is kind of like the chain rule. So you can see that over I you have all the different position derivatives, velocity derivatives, and dual dot t, the partial with respect to time. And what this means is that this you can just write it like this. If I substitute this equation by writing this as pi back to this, then you can see that dh dt is nothing but pi dot minus dou xi dot minus dou L by dou t, and this term is actually zero because of the Euler Lagrange equations. So again, if I'm going a little too fast, don't worry. You can just take these slides and see it again later. But essentially, if you see here, dou L by dou xi dot is nothing but pi dot is seen from the Euler Lagrange equation. So d by dt of pi is nothing but dou L by dou xi, right? And that's exactly what's given here. So I think I put a dot here by mistake. Shouldn't be a dot. Oh, no, no. Okay, wait one sec. Yeah, I think it's fine. Yeah, because dual. Yeah, this should not be a dot. I'm sorry. I'll remove it before I upload the slides. In any case, what happens is the term in the brackets, you can do the mathematics. The term in the brackets vanishes, and you get dh dt is minus dou L by dou t. And this tells me that if L is independent of t, which means the time independent Lagrangian, then H is conserved. And H, the Hamiltonian, is nothing but, again, you know this if you have taken a advanced classical mechanics course, the Hamiltonian is nothing but a measure of the energy of the system. So this is another way to say that if the system is independent of, it's symmetric under time translation, then we get this result that the energy is conserved. So this is another nice result, right? Time translation symmetry leading to energy conservation. So if we want to finally generalize this, if we have a symmetry, so right now we've seen it in terms of x and p and t and all that. But if you want to further generalize it, if we have a symmetry in our system such that the Lagrangian doesn't change when the coordinates, some coordinates q, let's not call it position or time or anything. When q goes to, let's say, q bar, where where q dash is some function of q, is q as some function of something, then that means that d by ds of this quantity is zero. Basically, if I change by some quantity s, then the Lagrangian doesn't change, and that's what this derivative is exactly showing. Then we have a conserved quantity which corresponds to C is equal to P dqs by ds. So again, you can set Q to position, changing in a linear direction, then this quantity will turn out to be the linear momentum. And you can try with all these things. You can find that, again, I think in the lectures you saw that this symmetry leads to this conserved quantity. You can actually validate that using this kind of approach. Can also prove this by just taking C, which I showed you in the previous case. So C dot will be nothing but P dot dq by ds plus P times dq dot by ds. P dot is nothing but dou L by dou q, and P dot, this is by Euler Lagrange equations, and P is nothing but dou L by dou q dot. This is by definition. And you can see that this is just d by ds of this, which is 0 by symmetry definition. So since c dot is 0, that tells me that it is a conserved quantity. So again, the reason that this is 0 is because this is symmetric under S. So if it is not symmetric under S, there's still some value. This won't be a conserved quantity. So you can see how the symmetry and the conservation of C are both tied together. And you can further generalize to time dependent symmetries. So far we have seen only symmetries which are, time independent. So that if it has a particular value, that value remains for all time. But actually it can be symmetric across with time dependence also. You can see that it looks slightly different than Noether's theorem. And there is a nice derivation of it. I'm not going through the details, but basically you have to just include an extra term which is related to the Hamiltonian, which is nothing but the energy of the system. So there are a few resources I have gotten here, which is all related to this concept of kind of putting together the Noether theorem. So if you guys are interested in this sort of thing, please go through this. And yeah, that's basically what I wanted to discuss. So just wanted to give some context for this. So again, if you haven't heard of Lagrangians before, those of you who are in BSc or whatever, don't be worried. You'll be learning them more in your course, and you'll also definitely learn about them in one of your master's level courses as well. Okay, or even maybe at your bachelor's level. I learned them in my master's, but I'm sure maybe some of you have encountered them in your bachelor's as well. It's just a very nice, in physics we have to be clear of what is physics and what is mathematics. Here this is a mathematical formalism that is very much motivated by this one physical principle, which is the principle of stationary action. So once you have this one physical insight, which is that particles follow the path that extremizes action or leads to stationary action, then from that you can build a mathematical format like this sort of form of the Euler Lagrange equation. This is actually something that comes from very old mathematics called the calculus of variations. So this actually has nothing to do with mechanics as such. It's just coming from mathematics. The physics part of it actually comes in recognizing that this system is connected to the stationary action, right? And we know that the path followed by a particle is is the one that leads to a stationary action. So you have to always, something I tell people when I talk about physics is that, there are problems which are physics hard, and then there are problems which are maths hard. So you should always understand where the challenges lie, right? Because physics is, the more and more advanced things you see in physics, you'll also get to see more and more advanced mathematics. So there are physics insights and there are maths insights, and try to, have a awareness of what is what, because that's always good to have. Okay. Anyway, that kind of brings me to the end of this lecture. Again, because of the first class, I didn't prepare much things. I just wanted to keep it light. But from next week onwards, I would really appreciate, for example, if you guys have things that you want me to particularly discuss, please drop me a mail again. This is my mail ID. I'll copy paste it in the chat again. So again, the sessions are going to be Monday from 6 to 8. So if you mail me by say Friday, I can incorporate into this next week's session. So again, it can be anything from the lectures. You can ask me to explain a concept again. For example, if you have particular problems you want me to solve, I can solve that, those kinds of things. You just send it to me so that I can discuss it in the class, so that if other people have had similar questions, it can be useful to them as well. Apart from that, let me just first copy paste my mail ID and put it in the chat. Um, okay. Apart from that, this is my website. I mean, there's a page on my website. So if you just go here, I've set it up so that you can find all the information. So as I said, these sessions are being recorded. I'll be uploading the recordings on my YouTube channel, and also the slides of the sessions I'm taking, I'll be uploading that as well. So I can just show you from one of the older classes I took. So, there'll be something like this where you can access all the sessions classes sorry, all the session videos, and also the slides will be given to you in a Google Drive, so you will be able to access them as well. So this is from like a previous Astro course that I taught in this capacity. So right now the links are broken, like they don't go anywhere. So because this is the first class, I didn't do it yet, but I'll be uploading the video and the slides by say tomorrow, so please check in, and you can find the resources. I think the NPTEL people will also be sharing the links with you. So again, I'm just sharing, just bookmark this and keep. Apart from that, that's it from my side. If you have any suggestions or questions at this stage, you can ask me. Or if you found this session useful, please let me know that as well. This is my first time teaching a particle physics course. I've taught astro and computer science courses before, but not particle physics. Okay, fine. Thank you very much. And thank you all again for joining on a holiday. Happy Republic Day to you all again. And if there are, okay, I can see few people are typing. If there aren't any questions, we can stop for now, but I can see few people are typing. Okay, fine. Okay, great. I'm really happy this was helpful. Again, if you have any other doubts throughout the week, please feel free to mail me. I'll mail you back or include it in the next week's lectures or something. Okay? Save all the things. Okay, thank you so much for joining. I'm going to end the meeting now. Bye, everyone.